All right, let's dive right into the anatomy of motion. Today, we're mapping out exactly how physicists view, calculate, and actually predict the physical reality of the universe. So whether you're gearing up for a university physics program, or you honestly just want to understand how things move around you, well, you are definitely in the right place. We're going to be climbing the concept building ladder in this explainer today. We'll hit the relativity of motion, distance versus displacement, graphing position, the true nature of acceleration, the mathematical beauty of the big five equations, and finally, solving some real-world problems. Okay, part one, the relativity of motion. This is all about defining where things actually are. So think about this for a second. How do you actually know something is moving? I mean, picture a NASA space probe flying past Neptune. Out there in the vastness of deep space, there are no road signs, right? To know that probe is moving, we have to compare it to a background. You literally can only know how fast an object's position is changing if you have a background that's either perfectly stationary or moving with a known velocity. And that brings us to a really fundamental definition. Before we even look at forces or, what pushes and pulls an object, we study kinematics. That's the study of motion without considering its causes. Now, to do this, kinematics requires a reference frame to serve as our coordinate system. For everyday engineering, the Earth is usually our stationary reference frame. But say you're analyzing a passenger walking down the aisle of an airplane mid-flight. Well, the airplane itself becomes your reference frame. Basically, everything is relative. Moving right along to section 2, distance versus displacement, how we measure motion. Now, in everyday conversation, we use the words distance and displacement like they mean the exact same thing. But in physics, they are entirely different beasts. Distance is a scalar quantity. That means it only has magnitude. It's just the total length of the path taken, kind of like the total mileage racking up on your car's odometer. Displacement, on the other hand, is a vector quantity. It absolutely requires both magnitude and a specific direction. It represents your exact change in position, which is calculated as your final position minus your initial position. So the crazy thing is, while the distance you travel walking to school and back adds up to, say, 10 kilometers of total steps, your displacement, because it includes direction, your total displacement would be exactly 0, since you ended up right back where you started. Mind-blowing, right? All right, section 3, graphing position. Let's visualize this motion. Take a look at this. Notice how the perfectly straight line on this graph instantly tells us the rolling ball has a constant velocity. When professional analysts look at a position time graph, where position is on the y-axis and time is on the x-axis, they are really just looking at the slope. Using a simple rise over run, so a rise of 40 meters east over a run of 10 seconds, that gives us a constant velocity of 4 meters per second east. So just by looking at the slope, we can read the physical reality of the object without even seeing it in real life. A perfectly horizontal line, that means a slope of 0, so the object is totally parked at rest. A straight line with a positive slope, that's cruise control, moving steadily away from the origin. A straight line with a negative slope means it's cruising back toward the origin at a constant speed. But the moment you see a curve on a position time graph, that is when things get interesting. That means the slope is changing. The velocity is not constant. Our object is either hitting the gas or slamming the brakes. Which leads us perfectly into section 4, the nature of acceleration. What happens when velocity actually changes? Acceleration is simply how many meters per second the velocity changes. Well, every second. And this example brilliantly illustrates it. A racehorse just exploding out of the starting gate. If that horse goes from rest, which is an initial velocity of 0, to a velocity of negative 15 meters per second, heading due west in a mere 1.8 seconds, we can easily find its average acceleration. By dividing the change in velocity by the change in time, we get an acceleration of negative 8.33 meters per second squared. That negative sign just confirms the westward direction. And hey, if we wanted to know the horse's exact acceleration at one specific millisecond, rather than just the average, we'd look at its instantaneous acceleration over a tiny, infinitesimally small interval of time. Okay, section 5, the big 5 equations. This is our toolkit for uniform acceleration. Welcome to what physics students affectionately call the Big Five. These 5 equations are derived from some pretty clever algebraic manipulation of our velocity and acceleration definitions. They relate 5 kinematic variables: initial velocity, final velocity, acceleration, displacement, and the time interval. Now, here's the secret. Notice how each equation deliberately leaves out exactly one variable. As long as you know 3 of the 5 kinematic variables, you just figure out what you are missing, and boom, you can instantly select the right equation to solve for your unknown. Honestly, this right here is the absolute foundation of mechanical engineering and physics problem solving. And finally, Section 6, Solving Problems. Let's look at some real-world engineering. So, how do professional crash test analysts and engineers actually use these equations in the field? Well, I'll tell you one thing, they do not just blindly plug numbers into a calculator. No way. They use a structured, deductive reasoning approach known as the GRASS method. This makes sure they carefully lay out exactly what variables they have before even touching an equation. Step 1 is given. List out your knowns. Step 2 is required. What exactly are we trying to find here? Step 3 is analyze. Pick the correct big 5 equation. Step 4 is solve. Do the algebra. And step 5 is state. Confidently declare your final answer with the proper units and direction. Let's actually put this into practice right now. Picture this, a high-speed collision at an automobile safety lab. A smart car, initially traveling at 100 kilometers per hour, slams into a solid barrier, crumbling 0.78 meters before coming to a complete stop. By listing our givens, we can perfectly select which of the big 5 will tell us the impact time, and really the horrific g-forces involved. But wait, look closely at step 3, analyze. Professional physicists always make sure their units match. So before you even start the math, that 100 kilometers per hour absolutely must be converted to meters per second. That is crucial. All right, now is your turn to apply the GRASS method. Imagine you are driving down the highway at a pretty brisk 137 kilometers per hour when suddenly you spot a police radar gun ahead. Yikes. You slam on the brakes, decelerating at 5.2 meters per second squared. I'm going to leave you with this real-world puzzle to solve using those big 5 equations. Convert your speeds, list your givens, and figure it out. Exactly which equation will you analyze with to find the minimum time needed to get under the 100 kilometer per hour limit and save yourself from a massive speeding ticket. Give it a shot. Until next time, keep exploring the incredible mechanics of our world.